thanks so much for the introduction. I'd say let's get started. So systems such as operating systems, cloud infrastructure, networking have historically been written in languages like C or C++, and have thus been rife with memory safety vulnerabilities. In fact, I had someone come up at the conference here and tell me that apparently Heartbleed's still exploited in the wild, which is crazy. These in turn have had a severe impact. For instance, the Chromium project reports that about 70% of their security critical vulnerabilities or bugs are the result of memory safety issues. And related bugs like integer overflows can even affect safety critical systems like commercial aviation. On that note, I'm Leon. As said, I'm a Ph.D. candidate at Princeton, and I traveled here by train from New Jersey. Thank you. And I'm a maintainer of the Tock operating system, which is an operating system that's written in Rust from the ground up. For those unfamiliar, if you have a Chromebook or a recent Windows laptop, there's a good chance that Tock might be running somewhere under the hood. And lastly, I deeply care about making software safe and secure. So as a developer of a Rust-based operating system, it won't surprise anyone here that I think we have a solution to the aforementioned issues, which is that safe systems programming languages, chief among them Rust, are safe by construction and can thus eliminate entire classes of vulnerabilities. And these languages have seen great adoption over the past few years. For example, we have Microsoft rewriting core parts of Windows in Rust. We have Rust being used to write Linux device drivers, and Google is adopting it for core parts of their Android operating system. And this is not just hype. This last move in particular also gives evidence as to the efficacy of these languages in real-world settings. So for instance, Google observed a significant drop in the number and severity of memory safety vulnerabilities since adopting Rust. Great, so let's rewrite all software in Rust then, right? That's the mantra. Well, not so fast. All of the systems that I've shown were carefully built by scores of engineers over decades. So rewriting this code is not going to happen overnight, if ever. And even when developers are building new programs from scratch, they typically rely on existing components, such as cryptography libraries, data stores, compression libraries, and anything else, most of which is probably going to be written in C still at this point. So in summary, rewriting everything is impractical. Even if we look past the prohibitive cost and time required to do so, companies might be lacking domain expertise. I mean, that's the entire point of using libraries in the first place. Or they might be forced to use certain languages as part of libraries that have undergone certification, which is really expensive or perhaps impossible to do for Rust at this point. So it's crucial that safe languages like Rust are able to interact with code written in such foreign languages, and that they are able to do this safely. So in this talk, I want to do two things. I want to talk about what exactly it is that makes interactions with foreign code safe or not safe. And then I want to introduce Omniglot, which is our research project that is designed to allow safely integrating arbitrary and untrusted foreign libraries into a Rust program. So let's dive into that first question. So when we look at the articles mentioned before, they all call out memory safety as the key property to the safety and security benefits that come with adopting one of these newer programming languages. But what does that even mean in practice, really? When we search for a definition of memory safety, we find that it's most commonly defined by negation, which is to say by stating behavior that must not happen in software written in a memory-safe language. For instance, the Internet Society defines memory safety as describing whether a software or programming language is designed to prevent memory bugs or vulnerabilities. And a recent report by the NSA and CISA lists some of these so-called memory bugs and categorizes them into, for instance, buffer overflows, use after freeze, data races, and use of uninitialized data. And this definition makes a lot of sense from a practical point of view, because all of these are examples of bugs which are prominent examples of how real-world software can be exploited and malfunction in practice. But when we use this definition to reason about software that is written in multiple different programming languages, we start to run into some issues. Ultimately, when we have a program that uses a foreign library, such as, for instance, a Rust application using a cryptography library written in C, then we want that entire program to meet this definition of memory safety. So it shouldn't contain any issues like use after freeze or out-of-bounds accesses. And to achieve this intuitively, we therefore need to make sure that all parts of the program are themselves memory safe. So in this example, with our host application written in Rust, we sort of get this guarantee for free by construction if we were a bit careful about our use of unsafe. For a foreign library written in C, that's probably more difficult in practice, but for the purpose of this talk, let's assume that's either been carefully checked or formally verified to contain no memory safety issues. But unfortunately, even under those assumptions, as we'll see throughout this talk, that alone is not sufficient. It turns out that even when we're working with two internally correct components, their interactions can still introduce subtle bugs that ultimately endanger memory safety of the overall program. And this is because those components must be able to communicate with each other, such as through function calls, return values, and most efficiently, shared memory. And it is this communication that can cause a composition of otherwise correct components to misbehave. So let's see an example of this. On this slide, we show a simple foreign function binding for a function named AES_encrypt. This function promises to encrypt a buffer that we provide as an argument, and then it returns a Boolean to indicate whether this operation was successful. And let's just assume that this function is actually memory safe, which more or less means that it only touches memory that Rust expects it to touch. So the buffer, the length, and the return value in this case. And additionally, we define a Rust enum called message with two variants, encrypted and unencrypted, and each one of them having a bit of associated data. So a Boolean and a vector for the encrypted type, and unencrypted having a C string. Our program will now call the AES_encrypt function, and then take that return Boolean and use it to construct a new instance of this message encrypted type. Unfortunately, even such a simple and commonplace operation can be risky in the presence of foreign code. And this is because of a clever and perhaps surprising optimization that the Rust compiler is able to perform called niche filling. When we look at the memory representation of this outer message enum, we expect it to have the following fields: a discriminant to indicate which variant is currently active, meaning encrypted or unencrypted, and then depending on that discriminant, a couple values. So for the encrypted variant, a value of type bool and vector, and then for the unencrypted variant, a value of type C string. But here, Rust recognizes that the Boolean only contains values in 0 or 1, and the enum discriminant also contains a mere bit of memory. I just need to distinguish between two variants. So Rust is able to merge those fields into one, where if that new field contains a proper Boolean, so either 0 or 1, it's going to assume that the encrypted variant is active and use the value stored in that field as its Boolean. And if it contains another uninhabited value, where it might choose, for instance, 2, it represents the unencrypted variant. And this optimization is super nice. It saves a word of memory, and it's just one example of the many optimizations that Rust is able to perform as part of its zero-cost abstractions. But it's tricky in the presence of foreign code. And that's because we actually had very few guarantees that a value returned by a foreign language like C adheres to Rust's particular requirements of its types. So for instance, for Boolean, that it only contains a value in 0 or 1. If C gives us an invalid Boolean, such as 2, then Rust will simply store that value in this field without any checks. And then upon a subsequent read, it'll mistakenly assume that the unencrypted variant was active, interpret a value of type vector as C string, and then read past the end of this non-null terminated buffer. So let's reflect on what just happened here. We took two memory-safe components interacting with each other, but then by exchanging an invalid value, we have caused Rust to perform an out-of-bounds access and have thus broken memory safety for the combined program. And to be clear, this is not really Rust's fault in any way. When we look at the Rust reference, it very clearly states that a Boolean can only contain values in 0 or 1, so that's a perfectly fine assumption for the compiler to make. And when foreign code hands us a value that does not meet these restrictions, then either foreign code or our bindings are incorrect. But what this does demonstrate, in my opinion, is that memory safety alone is not a useful property to talk about when reasoning about the composition of program components. It's not an aggregate property which only relies on a program's individual parts being safe, but a systemic property that arises from the interactions of those components. And so, instead, to build a safe foreign function interface, we also have to consider type safety and other safety-related invariants. So let's see what that would look like for a running example. First of all, as we've done before, we need to make some assumptions about the correctness of the foreign library itself. In particular, we need to make sure that the library only accesses memory that Rust expects it to access. So in particular, none of Rust's private objects that haven't been shared explicitly with foreign code. But then in addition to that, we must place restrictions over the interactions with Rust, such as ensuring validity of values. This requires us to make sure that all memory that is modified by a foreign library, but then exposed to Rust as a given type, to adhere to the restrictions that Rust places on that type. In this example, this is pretty straightforward. So for the Boolean, we need to ensure that it only contains values in 0, 1. And then this function also writes to the buffer. But because the buffer contains values of type U8, those are unconditionally valid values. Every bit pattern that could possibly be in this memory slot is a valid instance for the type U8. So we don't need to have to do any checks here. And then finally, Rust features an additional set of invariants related to its rule of aliasing XOR mutability, which can be particularly problematic in the presence of foreign code, especially when a pointer passed into this function can be derived from a Rust reference, but then stored and later used by the foreign library internally. We'll come back to this in a minute, but even this simple example should make clear that there are many ways in which a foreign function interface can break the combined program safety. And so using foreign libraries requires a deep understanding of and trust in the bindings and the library's code itself. So this had us thinking, is there maybe a way that we could do better? And to this end, in the second half of the talk, I want to propose a different approach. I want to introduce Omniglot, our research prototype and project and prototype framework that promises to mechanically uphold all of Rust's safety critical invariants across interactions with potentially untrusted and arbitrary foreign code. Before we can talk about Omniglot's mechanisms, we need to address the elephant in the room, which is that memory safety is indeed table stakes. And the assumption that we've made so far that any arbitrary foreign library is really memory safe is probably not one that we should make in practice. And so when linking against the foreign library, it generally runs in the same address space and at the same privilege level as Rust code. And thus, a buggy or malicious foreign library could easily break any of Rust's invariants simply by writing to its private object, or private objects rather. And so to address this fundamental issue, Omniglot uses a similar approach to a range of prior work, especially in the academic space, where we use memory isolation to restrict the address space accessible to foreign libraries, which is effective for preventing a number of bugs, like, for instance, Heartbleed, a typical sort of out-of-bounds access example, that would directly violate memory safety. But then to address the additional challenges that we want to highlight in this talk, Omniglot interposes on Rust's foreign function interface and mediates all interactions with foreign code to ensure that even untrusted foreign libraries cannot endanger Rust's soundness. In this talk, I want to go over two of Omniglot's key mechanisms, namely how it validates values and how it reasons about interactions with foreign memory. And we start by showing how Omniglot deals with potentially invalid values that are retrieved from foreign code. So on this slide, I'm depicting a simplified version of the same AES encrypt function binding from before. And we can see the C implementation here just returns 2. And with our knowledge of Rust's restrictions on valid values of type bool, we can see that this example is unsound. It introduces undefined behavior the instant that Rust receives a value of type bool, but that actually contains the numeric value 2. So to safely interact with arbitrary untrusted libraries, Omniglot must prevent such misbehavior before it can manifest an undefined behavior. And for this type of bug in particular, it uses a trick. Instead of invoking foreign code with its proclaimed type signature, we define another function binding with a weaker set of assumptions. And in this example, this could mean that instead of returning a type bool, we return a type ccar, which is a type of identical size and alignment to that of bool, but crucially without the same restrictions in terms of valid values. However, this value is also less useful. The developer expected to be returned a Boolean, and now they have to deal with an integer, so what's that all about? To address this issue, we generate a set of safe wrapper functions that invoke this set of weaker function binding internally, and then perform a set of runtime checks to try and recover the original type. If it happens to meet Rust's definitions and Rust assumptions, we can return that original type, and otherwise we can return a runtime error. So now developers can call this wrapper, which apart from forcing them to handle the possible type validation error, has an identical signature to the original binding. Okay, so the previous approach shows how we can deal with values that are located, that are provided by foreign code, but located in Rust's own memory. But next to these owned values, Rust might need access to values located in the foreign library's memory directly through references. And this exposes us to another prominent issue, namely that of upholding Rust's invariant of aliasing XOR immutability across foreign code. In essence, this rule states that there can never be two Rust references pointing to overlapping memory if at least one of them is a mutable Rust reference. This is a crucial property to uphold because Rust bases many optimizations on it, and violations of it have led to real-world exploitable bugs in practice. But at the same time, it's difficult because in many cases, developers don't really know what the library is doing, and so they can't really reason about the provenance of pointers as they're flowing through foreign code. Let's see a simple example of this. So here I have a simple stack data structure implemented in a foreign library, which exposes three common methods: push, peek, and pop. And let's just say that the host program wants to inspect the value at the top of the stack. So it calls peek, which returns a raw pointer, which can neither be safely read from nor written to, so it converts it into a Rust reference, and finally prints the value behind that reference. Now we want to modify the topmost element, so a developer just goes ahead and calls peek again, this time getting a raw pointer back and upgrading it to a mutable Rust reference, and then writing a new value to it. Unfortunately, this already breaks the invariant, because when we read the contents from the first Rust reference, we can see that the previous write operation has modified its contents as well, even though it's an immutable reference. And while this was predictable in the simple example, it's a stack data structure after all, which returns the same element if you don't change the stack. It's much harder to reason about for more complex libraries, so you might imagine a library giving you a pointer to an object and then another pointer to a field within that object. So in the worst case, we have to assume that all pointers that are issued by an untrusted library might be potentially aliasing each other. And so we must mechanically prevent developers from introducing any such unsound mutable aliasing. To solve this, we design a type infrastructure to model interactions with foreign memory that is able to statically reject such unsound mutable aliasing. We progressively gain invariance over foreign memory through type state transitions, and we start our type infrastructure from a pretty useful type, a raw pointer into foreign memory. It can be misaligned, dangling, or point to an invalid value and still not be unsound, so it can be safely exchanged between Rust and foreign code. But it's not really safely readable or writable, so we can't do much with it. To get an even more useful type, we can upgrade this pointer by validating that it is well-aligned and entirely contained within this isolated region of foreign memory that we assign to a library, which ensures that it cannot overlap with any of Rust's private objects. This then allows us to implement a safe write operation on it. And finally, if we want to read it, we can validate that this reference's pointee is a valid value using the same mechanism that we've shown before, which then yields a reference that is safely readable. We can also show all of these operations on more sort of a timeline here, where we say that we go from a raw pointer to a mutable reference, which then continues to exist, and then we validate that mutable reference into a readable reference. And while each of these operations is safe in practice and in isolation, and it's nice because we have a read primitive and a write primitive for our foreign library's memory, if we combine them with some other operations that Omniglot exposes, this can again result in unsoundness. For instance, when we invoke foreign code, we give control to the foreign library. It can, of course, write to all of its memory. So if we validate a Boolean that is located in foreign memory, and then the library writes a value 2 to it, then we have sort of a time of check, time of use issue here, because the invariants are no longer valid beyond that point, but the type continues to exist. Similarly, when we revoke memory allocations of active mutable references, that would make them dangling, and so we have a very classical memory safety vulnerability again. So to solve this, we must temporally constrain the time that Omniglot's references are live for, and we do so by introducing two new marker types, which are called allocation scope and access scope. Allocation scope is represented as an orange square, and access scope as a blue triangle. These are singleton types, which means we can only have one instance of these types per foreign library. And we then use them to bind Omniglot references to the lifetimes of these Rust types, of these scopes, to ensure that we avoid these dangerous operations. For instance, the validate operation now takes a shared reference to this access scope marker, which causes the resulting types that are produced here to be bound to the lifetime of that marker. This ensures that it cannot outlive the point at which we take a unique reference to the same marker, which we do now in the invoke operations and the write operations, which are the two types of operations that can endanger the invariant of the value that is pointed to being valid. Then the Rust borrow checker for us ensures that no validated references can live past the point of any of these dangerous operations. And we illustrate this here on the timeline here because this type sort of ceases to exist at this point. Finally, we use the same approach for mutable references. By binding those to the lifetimes of an allocation scope marker here, and then requiring all operations that free memory to take a unique reference to that marker, then we ensure that no such reference can outlive its underlying allocation. Okay, so that was a lot. So let's see how these new types change the stack example from before. We can still inspect the stack's topmost element, this time by upgrading this pointer and binding it to an allocation scope, and then validating it to bind it to an access scope, and finally printing its value because this is a readable type. We can also write to this memory in a similar way. However, note that this time around, in the write operation, we take a unique reference to the access scope. This conceptually closes the scope that was active up until this point, and then immediately reopens a new one after that operation. But then, finally, when we now try to access the previous reference, we get a compiler error. This is because the reference is bound to the previous access scope, and it automatically becomes inaccessible after issuing this write, which has closed that scope, and thus eliminates unsound mutable aliasing. Okay, so this concludes our exploration of two of Omniglot's core mechanisms, and I invite you to read our OSDI 25 paper for a more in-depth set of details on how these mechanisms work. But I want to briefly pop up a bit and talk about what all of this is useful for. So we implement Omniglot as a set of crates that provide common traits and types, and modify Rust bindgen to generate a set of Omniglot-compatible bindings for C header files. And then these crates need to integrate with a set of Omniglot runtimes that then enable us to bridge this with the memory isolation mechanism we use to sort of provide general confinement and memory safety for these libraries. We implement one such runtime for the Tock operating system kernel, an operating system that's security-focused and often used for hardware root of trust purposes. And these, in particular, often need to use existing certified libraries. And we implement runtimes for Linux user space, for instance, using x86 NPK, which is a relatively recent Intel and AMD processor feature. Because this mechanism itself is not particularly secure, and maybe also in our implementation, we're currently in the process of porting to a software fault isolation-based mechanism that should get rid of some of these issues and be a more portable solution. As Omniglot does add safety guarantees, it introduces overheads. And to quantify these, we evaluate against existing work. So here we can see the performance of a libpng image decompression routine as a function of the image size, using both Rust's native foreign function interface and using Sandcrust as an alternative approach that delivers equivalent soundness guarantees by using process isolation and inter-process communication to sort of sandbox a library in a different process and then serialize the data and shuttle this between those two processes. As you can see, Omniglot significantly outperforms this approach simply due to its ability to interact with foreign memory directly without any copying, serialization, or context switch overheads. And so this concludes the second part of the talk about Omniglot. Today we've done a deep dive on Rust's foreign function interface and how our research prototype can maintain soundness even in the face of untrusted foreign code. And while I do think that Omniglot is in itself an interesting and promising approach, I think that there are some more important high-level takeaways that I want to emphasize and maybe have you take away from this. Which is that, first of all, I think we need safe foreign function interfaces. Foreign libraries will not go away anytime soon, and Rust safety guarantees are only as good as the weakest link in the chain. So as long as you have one single library sort of in your compilation unit, we need to ensure that these interactions are actually safe and don't break Rust soundness. But to achieve this, we need to look just beyond memory safety of the foreign library itself. Memory safety really is just table stakes, and the composition of Rust and foreign code must be sound, which in particular means that we need to pay close attention to not breaking any of Rust's other invariants. But this is a hard problem in general for arbitrary complex libraries. And so with this talk, I'm advocating for more systematic approaches to maintain these invariants across the foreign function interface. In fact, I'm not the first one to propose this. There are many other prior approaches. For instance, a recent academic contribution proposes to extend MIRI with an LLVM interpreter to find and fix memory bugs and aliasing issues across such interactions. Yet others are looking into establishing a formal semantics for interaction between two languages, which helps reason about these types of problems in a rigid and automated way. And even the Rust ecosystem itself features many projects like CXX or Wasm BindGen that bridge higher level types of other languages into Rust. And while these approaches, many of them, don't address issues like aliasing or memory safety bugs in foreign code directly, they do make it much easier to express rich and correct foreign language bindings, which can go a long way in making these bindings safer in practice. And today, I presented Omniglot, which is our take on this issue. It maintains soundness without assumptions about the foreign library by interposing on Rust's foreign function interface, integrating with memory isolation primitives, and mediating interactions with foreign code to provide memory safety and type safety efficiently. And as there won't be a single one-size-fits-all solution to this larger issue, I'm looking forward to, especially here in the conference, discussing on how we can ensure Rust safety, even though foreign libraries are here to stay. Perhaps maybe in the breaks here, I'm happy to chat about this, or online on the Discord. And lastly, here are links, or rather QR codes, to our research paper, which goes into much greater details, as well as our prototype implementation. It's a research prototype, so it has a couple rough edges. If you do want to try it out, be sure to send me a message, maybe on Discord, on all the other channels, and I'll be happy to help you get started. And with that, I want to thank you all for listening, and I'm happy to take any questions. I think we should have plenty of time.
I may have missed it in your presentation, but you mentioned an isolation mechanism, and I had understood that to be a address space isolation. Could you reiterate the piece you're talking about? If you don't mind.
I guess we say that we make portions of the address space inaccessible. It's really a memory protection mechanism. So you could imagine unmapping some pages to make them inaccessible while we're executing foreign code. The protection mechanisms that we use in practice are the RISC-V physical memory protection, PMP, if that rings a bell, or as we said now, MPK on x86, which allows us to make certain memory pages inaccessible while we're executing some code. And what we're now porting towards is software fault isolation, which doesn't rely on any hardware mechanisms. It does binary rewriting of the foreign libraries to make sure that it is contained within a given portion of the address space and can't use any memory reads or writes outside of that portion of the address space.
Hey, hi. Thank you for your talk. A question, is the mem address separation part optional? In our use case, we don't really care. We control both the C and the Rust library. And if, yeah.
I think that's an interesting question. I think there's certainly a model of this where we wouldn't need to rely on memory isolation, and you can still get benefits by doing some of the type validation and perhaps even reasoning about aliasing. I haven't done like a really formal analysis of what that would look like and where the pitfalls would be. So I think, obviously you couldn't sort of unconditionally guarantee soundness under that model.
When you were doing the example with the Boolean return result, in the wrapper you had it checking for 0 to 2. Is that slideware, or how deep do you look in analysis to generate your wrapper?
So these implementations, sorry, I'm trying to find the slide here. I believe that should have been like a less than 2, but it might possibly, so it's like a larger or equal 0 and less than 2. So it should check for 0 or 1. These implementations are currently written manually as part of a trait that we implement for given types. So if you have any higher level types that carry higher level invariants that you want validated, you would just simply implement that trait. It's an unsafe trait because obviously our soundness sort of depends on the correct implementation of this. But yeah, that's not auto-generated at this point.
Hi there. Thank you for coming all the way from Jersey. Appreciate it. I had a question. I come from a company in the energy sector, and we have mountains of C++, and I am very interested in being able to interoperate with that C++. It would be a little bit different, though. I feel like the focus of your work, which is awesome, is more about Rust applications that are utilizing existing libraries, where in my company, it would be more applicable to say that we're trying to bolt on some Rust to these large existing C++ code bases. Could Omniglot be used in that situation where maybe like C++ is in the driver's seat and Rust is kind of the library?
Yeah, I think you raised a GitHub issue, and I appreciate that, and I was gonna reply to that. But that's an interesting question. Ultimately, our solution depends on Rust being at a higher privilege level than foreign code, or foreign code from the perspective of Rust. And that's because we want to prevent this code from accessing any of Rust's private objects to avoid breaking any of its soundness invariants. If you could elevate your code into a higher privilege level, even in a larger program, and then provide what I think typically in academia is known as a trampoline into that, I think that would be possible. Our solution, I don't think, would support that out of the box. It would probably require some tweaks to our infrastructure.
You mentioned in passing kind of almost an analogy to WASM bindgen. One annoying thing with WASM bindgen is all the memory keeps getting copied over and over again, and that gives us safety, but at probably that 2-to-1 cost. Is there a hope that your approach could help make WASM bindgen so we can actually share the memory between the JavaScript world and the Rust world?
I mean, that'd be awesome. I haven't looked into this. Presumably because in WASM you have these memory objects and they're just mapped somewhere in your program's memory. As long as that's accessible, I don't see a particular reason for why we couldn't use these exact mechanisms to have sort of safe Rust references into the WASM memory without copying. That's certainly something that I'd be super interested in exploring. I haven't really gotten to that yet. Oh boy. Okay, it's controlled by garbage collector on the JavaScript side. Well, that might be a bit more of a tricky issue then.
Hi, thanks for the talk. I have sort of 2 quick questions. One is, I don't know a lot about this, but my coworker who's remote asked, is there any possibility that this would integrate well with Cherry, the RISC capability hardware enhanced memory protection?
There may or may not be a follow-up research project exploring that. Not really any concrete things to share yet, but it's on the roadmap. I mean, we're happy to take funding. My advisor's in the audience, so if anybody is particularly interested in this.
And the second part is, I know this, you presented the paper, and it seems like there's still a lot of research going on. But you mentioned the Tock OS, and so I guess the question is, are you actually using Omniglot in Tock OS as it's in production?
Not in production right now. The original motivation for this was actually for the hardware root of trust use cases, because we had a company which was really interested in using their existing sort of certified or I'm not an expert in like industrial certification certified library as part of Tock, which is an operating system that derives many of its safety guarantees from the Rust language. We do most of our isolation in between kernel components based on language level isolation in Rust. So obviously you have this tension between needing to comply with certification requirements, most of which are written with C in mind, and then having all of these safety guarantees in practice rely on Rust soundness. So that's kind of where this originated from, and I think that's still on the roadmap. It's just that obviously we had it's a long journey getting here and getting this working. But now that the paper is out, we're looking forward to getting this a bit more polished and upstream, perhaps. All right, thanks so much.